Okay, so our new topic is surface integral of a vector field, right? Before we get into the actual surface integral, right? Let me note something about a surface. That a surface, a parametric surface, or a surface that's otherwise defined, right? What we can do is we can assign a direction to a surface, right? Okay, so this is the first thing we want to discuss, right? So let's recall something that we saw in the case of a parametric curve, right? Right. So in the case of a parametric curve, such as this parametric curve, which is outlined in blue over here, right, which is given in blue, right? Notice this parametric curve, what it has a particular direction associated to it, right? And this direction, what you're doing is you're going around this parametric curve, which is simple and closed, right? We're going around this parametric curve in a counterclockwise direction, right? Okay, so how you indicate the direction for this simple closed parametric curve, right, is these arrows over here, right? So this blue arrow here on the blue curve, that is indicating the direction, right? Notice there's a next blue arrow over here and the next one here, and these are all indicating that you moving around this curve in a counterclockwise direction, right? Okay, so this simple closed curve has a direction or orientation associated to it, right? And we saw previously that if we have a simple closed curve, what's considered a positive orientation for a simple closed curve is in fact the counterclockwise direction, right? The main thing I want you to get out of this is that if I have a parametric curve, you can assign a direction to it, right? Okay, so for example, this parametric curve here, if you want to assign a direction to it, you could simply just indicate the direction by an arrow, right? So an arrow here would indicate that you're starting over here and you're ending over here, right? And in this case over here where the arrow is already drawn, right, the arrow is indicating that the direction is counterclockwise direction here, right? So the direction that you're choosing for this parametric curve is in fact a counterclockwise direction, right? Okay, so now what we want to do is we want to consider a similar idea, but now for surfaces, right? So we want to assign an idea of a direction to a surface. Alright, so now if I have a parametric surface, right? If I have some surface, how would I actually assign a direction or orientation to this parametric surface, right? Okay, so for example, this parametric surface over here with the 2 cos theta, 2 sin theta, and z over here, right? We saw previously what this is a cylinder centered around your z-axis, right? So that's the cylinder over here. Okay. So it's a cylinder centered around a z-axis of radius 2, right? And the height is going from z is equal to 0 to z is equal to 3, right? Okay, and what we want to do is we want to somehow give this this parametric surface, we want to assign a direction to it, right? Now, how are you going to assign a direction to this parametric surface? Well, okay, so for simplicity, this cylinder over here, right? It has 2 standard directions if you want, right? The 2 standard directions is that you could be heading outside of the cylinder, right? So you're pointing outside of the cylinder, so that would be one direction. And in a diagram, what you do is you'd use normal vectors to indicate that you pointing out of the cylinder, right? So such as this over here. Okay, so for this cylinder over here, what you want to notice is that you have normal vectors that are actually pointing out of the cylinder, right? And if you look at a plan view, right, you get a better picture over here. You see that you have normal vectors that are pointing out of the cylinder, right? Okay, so what these normal vectors are doing for you, right? These normal vectors over here, right? What they're doing is they assigning a direction to the cylinder, right? And it's saying, well, we're gonna choose a direction, and that particular direction is in fact pointing out, right? Okay. Right, so that is one direction that is associated to the cylinder, right? And such a direction for a surface, right? And the cylinder is a surface, so such a direction for the surface is called an orientation, right? Okay, so one possible orientation is uh, when you actually pointing out of the surface, right? So out of the cylinder, right? Okay, so our next possible orientation over here is instead of pointing out, right? What you could do is you could reverse all these arrows, right? So if you reverse all of these vectors, these normal vectors, what you're now going to do is you're now going to point in, right? Okay, so you see that your vectors are pointing in, and if you're looking at the cylinder, right, for each point on your surface, the normal vector instead of pointing out is actually pointing in, right? Okay, so what this is saying now is that the direction that you're choosing for the cylinder in this case, right, is a direction that's actually pointing into the cylinder, right? So this direction where you're pointing in, this is one possible orientation, and the other previous orientation is when you're pointing out, right? Okay, so for a cylinder, what you have two possible orientations for the cylinder, right? What you could do is you could either point out of the cylinder or you could point into the cylinder, right? Or you're pointing out over here, right? What you're doing is you're using normal vectors, right? Okay, and we in fact already saw how to get normal vectors for a parametric surface, right? And I'll show you the calculation in a second, right? But the point that I want to make is you have two directions, right? One is pointing out and one is pointing in, right? And in the case of when you want to specify the direction that's pointing out, right? What you're going to do is you're going to use normal vectors at each point on your surface, and those normal vectors, and you want those normal vectors to vary continuously, right? So notice that they're not jumping in. You don't have some pointing out and some pointing in, right? All of them nicely all pointing out, right? So the vectors more precisely are assigned in a continuous fashion to the surface over here, right? So you don't have any kind of strange behavior where the vectors are, say you have this vector pointing out and you have one just below it pointing in, right? All vectors are in fact pointing out, right? So this sort of smooth assignment of normal vectors, what it will do for you is it will assign a direction for the surface, and that's an example of an orientation, right? Okay, so this is one possible orientation. If I reverse the direction of these vectors here, right, by introducing a minus sign here and a minus sign here, which I did already, right, then that would give you a second orientation, right? Okay, so what an orientation is for a surface is an orientation is assignment, a continuous assignment of unit normal vectors to each point on the surface, right? And you're seeing on this surface over here at each point what you have is you have a unit normal vector. Okay, so let's look at this definition, which would summarize what I just said, right? So I have some surface S, which an example of a surface S is the cylinder here, right? And a surface S is orientable. It's called an orientable surface if you have a continuous function that assigns a unit normal vector to each point of S, right? Okay, so it's an orientable surface, or it's going to have an orientation, right? If you can assign a unit normal vector to each point on the surface, right? And you notice over here, we can in fact assign a unit normal vector to each point on the surface over here, right? Okay, and such an assignment of a unit normal vector to each point on the surface, right? And we call in that n, right? That's in fact an orientation of a surface S, right? Okay, so a surface S, such as this red cylinder over here, is an orientable surface if there's some function that's defined on the surface, such that at each point on your surface, the function is gonna assign a unit normal vector to each point on the surface, right? Okay, so that function is called small n over here, right? Small n is for normal, right? And if that such a function exists, right, then it's called an orientation of your surface S, right? And you have two possible orientations for any orientable surface, right? Okay, so you do have a function S that's going to assign a unit normal vector to each point in S, right? So it's the function that's going to assign a normal vector, each of these normal vectors. Yeah? Okay, so it's the function n that's going to assign a unit normal vector at each point. So that's going to be a small n, right? Okay, and you have two possible orientations for any orientable surface, right? So either your vectors, in the case of the cylinder, right, they'll point in one direction out of the surface, and then the next possible direction that you can get is simply by taking these normal vectors and then just taking the negative of each of them, right? And when you take the negative of each of them, your orientation is going to reverse, right? Which means that now what's going to happen is unit normal vectors are now going to point in the opposite direction, right? And in this case for a cylinder, right, what it's doing is the opposite of the outward normal vector would be inward normal vectors here, right? So how do we actually get these unit normal vectors, right? So let me reverse these so that they point in out. Okay, so how do I get these unit normal vectors? Well, in fact we saw already how to get normal vectors for a cylinder, right? And what we saw when we were considering parametric surfaces is we were actually getting unit normal vectors at any point on your parametric surface, right? So if we can get it at any point in the parametric surface, that's actually exactly what we're looking for, right? We want to be able to get unit normal vector at any point on your parametric surface, and how we did that is we use this formula, the r theta cross rz, right? So a reminder as to what the r theta and the rz is the r theta is what you get by taking this r over here and differentiating each of the component functions with respect to theta. The rz is what you get by differentiating each of these component functions with respect to z, right? And what the r theta and the rz will do for you, right? It's actually giving you tangent vectors along your surface S, right? So in this diagram here, right? So this is the same cylinder, right? Your height of the cylinder, this height of the cylinder should be 3. Right, so your height of cylinder is 3, radius here is 2, it's centered around your z-axis, right? Okay, and in this diagram, okay, this vector here, this is a normal vector, right? You can probably see the small n over here, this is a normal vector, right? And this is r theta here, and this is rz over here, right? So r theta cross rz, right, what that is going to give you is that's going to give you a normal vector, right? So our formula for getting the normal vector at any point is using r theta cross rz. Okay, and we saw previously how to calculate that. As I said, you get the r theta by differentiating your component functions here with respect to theta. So you're going to get a minus 2 sine theta and a plus 2 cos theta and a 0, right? The rz is 0 here, 0 here, and 1 here. You take the cross product of the r theta and rz, and you're going to get 2 cos theta I plus 2 sine theta j, right? And that, in fact, gives you a normal vector, right? Okay, so that gives you a normal vector. 2 cos theta I, 2 sine theta j would give you this normal vector, right? Okay, but there's one small issue over here that in our definition for an orientation is that the orientation is supposed to assign unit normal vectors at each point, right? Okay, so in this diagram here, right, what I have is at each point on the surface, I have a unit normal vector, right? But what I have over here so far in this calculation is 2 cos theta I plus 2 sin theta j, right? Now, if you take this vector is not a unit vector. This vector, in fact, has length 2, right? Because if you take the length of this vector here, right, what you're going to get is you're going to get 4 cos squared theta plus 4 sin squared theta, right? So you get the square root of 4. So the length of this vector is in fact 2, right? So this is good, right? What it's given me is given me a normal vector at each point, right? So it's given me a normal vector. It's given me a normal vector at each point. Okay, but it's not given me a unit normal vector, right? So in order to get the unit normal vectors from this, right, what I do is I just divide the vectors here by their own length, right? Okay, and I already worked out that the length of each of these vectors is 2, right? So what I'm going to do is I'm going to divide this function here that gives me my normal vectors, right? Divide that by the lengths, right? And that would give me, well, I'll have a 2 down here, and that 2 will cancel with the 2 over here and the 2 over here. So I'll get cos theta I and sin theta j, right? What you want to notice now is that each of these are actually unit vectors, right? Okay, so these are unit vectors, and for your various parameters theta and z, right, what that will give you is the various parameters theta and z give you different points on this parametric surface. So at different points on your parametric surface, what you're going to get is you're going to get the corresponding unit normal vector for that point, right? So for example, at this point over here, you'd have a certain unit normal vector. At this point directly on top of it, you in fact have the same unit normal vector. And say at this point over here, you're going to have a different unit normal vector, right? So at each point on your parametric surface, you in fact found a formula, right? Or more precisely, you found a function that is giving you a unit normal vector at each point, right? Okay, and such a function that gives you a unit normal vector at each point. That's an example of an orientation of the surfaces, right? And as I mentioned previously, you really want to view the orientation as you have a surface and it's assigning a direction to the surface, right? And you're going to have 2 possible directions. In the case of a cylinder, it's either pointing out of the cylinder or it's pointing into the cylinder. Alright, so we saw what it means for a parametric surface to be oriented, right? It has a certain direction associated to it, right? Okay, so a cylinder over here has a particular direction, and in this direction that's specified over here, the direction is pointing out of the cylinder, right? Okay, so I have a smooth parametric surface S over here with an orientation that is specified for it, right? And the orientation is specified by calculating RU cross RV and dividing by the magnitude of RU cross RV in order to get unit normal vectors, right? And we actually just did a calculation of that, right? In the case of this cylinder here, right, where we had parameter variables theta and z, right? The r theta cross rz was 2 cos theta I plus 2 sin theta j. And when we divide by its own length, we get cos theta I plus sin theta j, right? Okay, so this gives me an orientation which is pointing out like this over here for the cylinder, right? Okay, so what I have for my definition of my surface integral is I'm going to have some smooth parametric surface, such as this one over here, right? I'm going to have an orientation for it, right? Which is okay, so I'm going to have an orientation for the S that in fact is inherited from the parametric description over here by, okay, so once you have this parametric description, what you're going to do is, in order to get an orientation, you're going to just take RU Going to take RV, take the cross product of it, and then divide by its length, right? So any parametric surface, such as this over here, is going to have a standard orientation associated to it, right? It may not be the orientation that you want, right? But it always will have an orientation that's associated to the parametric surface, right? So in this case, this parametric surface over here, right? When you work out the r theta cross rz and you divide by length, what you have is you have this orientation, which is a nice orientation, right? It in fact points out, right? But if you have a parametric surface specified like this would always give us an orientation, right? The issue is whether the orientation is going to point in the correct direction, right? And we will see an example of that in a second, right? But for the time being, what I have is I have a parametric surface and it's oriented, right? It has some direction associated to it, right? And what I want to do is I want to calculate the surface integral of a vector field over that surface S, right? And how I'm going to do it is I'm going to use this formula here, right? Notice, so this is notation over here is for the surface integral of a vector field, right? The F over here is your vector field, right? The N over here is the orientation, right? So an example of an orientation of an N over here is for this cylinder over here. The orientation is the blue arrows here, right? Okay, so your vector field is not in fact shown in this picture here, right? All you're seeing is the orientation, right? Okay, so I'm going to have some vector field, right? So anyway, so for surface integral, this is your notation for surface integral, right? You're going to have a vector field, you're going to have an orientation, and you're going to have your surface S, right? So the surface S, an example of the surface S is this red cylinder over here. An example of an orientation is the blue normal vectors here, right? Okay, and what you're going to be doing is you're going to be integrating a vector field over such a surface that's oriented by these blue normal vectors here, right? Okay, so as I said, it'll be helpful to see what the vector field is, and I'll do an example in a second where you'll in fact see the vector field, right? So if you want for this surface over here, you're going to have two different sets of vectors, right? What you're going to have is you're going to have the normal vectors for the surface, and then you're going to have the vector field for the surface, right? And you're going to be taking the dot product of those two different vector fields on the surface S, right? Okay, how we're going to work out the surface integral of a vector field over the surface S, right, is similar to what we did to work out the surface integral of a function over S, right? Okay, so notice over here what I have in this case is a vector field. What we saw previously was a function that was defined on my surface S here, right? Okay, but so how are we going to work it out, right? So over here what we did is we used the parametric description that was given to us, right? So wherever you see the x, the y, and the z, right, you replace it by the corresponding functions in your parametric surface. So likewise over here you're doing the same thing, right? Where this would be a vector field which would have x, y, and z in it, right? And everywhere you see the x, y, and z here, you're going to replace by the corresponding functions in your vector field, right? Okay, so that's the first thing that you're going to do. Then the next thing is you need to work out the RU cross RV, right? Okay, so for these problems, you don't actually need to work out the orientation beforehand, right? Unless you really want to check to see what the direction is for the surface, right? So if you're doing a calculation, you're really just using this over here, right? So anyway, so if you're doing a calculation here, you'd need the RU cross RV, right? And that's the same RU cross RV that I had for surface integral of a function, right? So it's the same calculation. Over here, what I did is I took the length of the RU cross RV, right? Over here, I'm not doing that. I'm keeping the RU cross RV as vectors here, right? Now, when I work out what this is here and I put in the component functions and so on, right? This big F on this side over here is giving me a vector field, right? That's defined on my surface S, right? And this over here is also giving me a vector field, right? Okay, and what I'm doing here is I'm taking dot product of the vectors in the vector field, right? So at each point, I'm going to have a vector here. I'm going to have a vector here, right? And then what you do is you take in dot product of the vectors. So this, well, that is what this notation is, right? I have vectors here. I have vectors coming from the RU cross RV, and I'm going to be taking a dot product of that, right? Now, when I take a dot product of that, right, what I'm going to end up with is just a function in terms of u and v, right? And now, when I have that function in terms of u and v, I'm going to do a double integral over r, right? Okay, so in that sense, that's similar to what I have over here, right? Once I put in my information over here and I work out the length of the RU cross RV, right? What I end up with is a function of u and v over here, function of the parameters. And then I do a double integral over r, right? So likewise, it's the same thing over here, right? When I work out my dot product here, I'm going to get a function of u and v, and then I would work that out as a double integral over r, right? Okay, so it will help to see an example, which we will see now, right? Alright, so let's work out this surface integral of the vector field that's given inside here, right? So the vector field is 2xi plus 3xzj, right, plus y squared k, right? So this is your vector field inside here. And your parametric surface is specified for us, right? Your parametric surface is the ui 1j vk, right, where your parameters u and v lie between 0 and 1, right? Okay, so this parametric surface, we saw what this is already, right? This, in fact, is a truncated plane, right? Okay, so I'll show you some diagrams that's illustrating all of this, right? But the first thing I want you to get is that this here is an example of a surface integral, right? So you have a vector field, right? So this is your vector field over here. You're integrating over a surface S here, right? You're integrating over a surface S over here. And this surface S over here, in fact, has a direction or orientation that comes from this expression, right? The RU cross RV, right? Okay, but when you're working out this, to work out the surface integral, this would be your formula here, right? You see in the RU cross RV, right? So the orientation, in fact, comes from this over here, right? The RU cross RV over here, right? Okay, so your parametric surface that you're going to be integrating over the truncated plane will have inherent orientation associated to it, right? Which comes from the RU cross RV, right? Okay, so let's see what these vector fields and the orientation and so looks like, right? All right, okay, so what the parametric surface looks like over here is a truncated plane, right? So this is part of your plane y is equal to 1, right? Okay, so this green axis here is your y-axis, so your truncated plane is lying in the plane, and notice over here you see the y is equal to 1, right? And then looking at it this way, the x goes between 0 and 1 and the z goes between 0 and 1, right? So this is a truncated plane. And we saw this several times already, right? Okay, so that's what the S is, right? And what we also want to get an idea is what this vector field is, right? Now, this vector field doesn't really have any sort of nice symmetry in it, right? Okay, so and then really what we care about is how the vector field is cutting across this surface S over here, right? Okay, so, well, what is the vector field going to look like, right? The vector field, if you sketch it for the entire three-dimensional space, right, it will look like this, right? Okay, so this is what the vector field looks like. It doesn't have any particularly nice symmetry, as I said, right? But this is what the vector field is, right? Okay. Right, but what we care about is the vector field as it cuts across the surface S, right? So what we care about is the vectors that actually lie on the surface, that, well, not lie, but that at each point on S, right, what you're going to have is a vector from the vector field, right, from the vector field F, right? Okay, so this is the vector field in the entire three-dimensional space, right? What we want to see is we want to see the vectors that are actually cutting through the S here, right? So we can see that here. Okay, so the vectors from the vector field that actually cut across, cut in through the S over here, right? You see, and it's illustrated here, right? Okay, so the blue arrows here are the vectors, right? And this red surface over here, this is your truncated plane, right? So the red surface here, that's the S, right? And the blue arrows here, that's your vector field, right? Okay, now what your surface integral is doing for you, right? If you're thinking of the vectors over here as representing velocity of fluid flow, right? So let's go back to the big picture. Okay, so in this big picture here for this vector field, which is the same vector field in this picture here, right? Okay, what you could think of is that you have fluid flowing in three-dimensional space, right? And at each point in three-dimensional space, so you have fluid flowing in three-dimensional space, and at each point in three-dimensional space, you're going to have a velocity vector for the fluid at that point, right? Okay, so this vector field describes the velocity of fluid flow, right? Okay, so going back to this picture here, right? Right, so you have your fluid flowing, right? You think of this surface S here as being some sort of permeable membrane, right? So if you want, it's like a mesh, right? So the fluid could in fact just flow straight through it, right? The parametric surface, the S over here, doesn't present any sort of obstruction to the fluid flow, right? And what you're trying to calculate is you're trying to calculate the amount of flow through this parametric surface S over here in unit time, right? So flow per unit time, or you could look at it the next way as flux, right? But we're not going to use the word flux. We could just think of it, if you're just thinking as fluid flow, well, then what we're trying to calculate by your surface integral, right? So what we're trying to calculate by this surface integral, is right, we're trying to calculate the flow through your surface S over here, right, in unit time when you're regarding your vector field as velocity of fluid flow, right? Okay, so you see the S over here, so your parametric surface, this is the S here, right? Okay, and we see in the vectors now, right? The vector field is at least the vector field for the surface S, right? So the vectors that are cutting across your surface S here, right? Those are shown by your blue vectors here, right? And then the last thing that I would need if you want in this picture is the N here, right? So, well, the N over here is telling you what the direction of this surface is here, right? Now, if you notice in this picture, right, you might be, if you're looking at this picture over here and you're looking at, say, the flow through this surface S through your truncated plane over here, right? You'd be inclined to think that yes, the net flow would in fact be positive, right? Because everything seems to be just moving in this y direction over here, right? But unfortunately, so I mean, yes, that is correct in some sense, right? But you see this parametric surface S over here, it could have two possible orientations, right? And it might be natural to say that the orientation is just in the y direction here, right? But you need to specify that somehow, right? And this integral here, it doesn't specify the well, it specifies an orientation, but it may not specify the orientation that you want, right? And we're going to see that now, right? The orientation that this and the orientation that the surface S remember how you get in this orientation, right? How you get in the orientation is via RU cross RV, right? So it's entirely possible this RU cross RV could give you the wrong direction, right? Okay, a direction that you don't want, right? In this case, nothing is wrong here because it didn't tell you to specify any particular direction, right? They just tell you to work out the problem, right? So when you work out the problem, you just get an answer, right? But sometimes you may want to specify a direction for S over here, right? So in that case, you'd need to be careful about your orientation, right? Anyway, so, well, okay, so what do we have so far, right? What we have is we have your surface S over here, right? You have the vector field, which are the blue arrows here. And now what we want to see is we want to see the orientation, right? So the orientation you want to remember, as I said, you're going to get by calculating the RU cross RV, right? Okay, by calculating this RU cross RV, right? And dividing by the length if necessary, right? Okay, so what would be the orientation for this, right? Well, you can work it out here, right? This is the parametric description, and we saw this calculation already. The RU is when you differentiate each of your component functions here with respect to u, right? So what you're going to get is you get a 1 over here, you get a 0 over here, and you get a 0 over here, so you're going to get an I here. The RV would be 0 here, 0 here. And okay, so you differentiate with respect to v, so you get 0 here, 0 here, and 1 here, right? So 0 here, 0 here, and 1 here. Alright, and then you work out the RU cross RV, right? So that's what you need in your formula for calculating surface integral of a vector field. You need the RU cross RV, and the RU cross RV is minus j, right? And remember, the orientation is RU cross RV divided by the magnitude of RU cross RV, right? Now the magnitude of RU cross RV over here is in fact 1 because minus j is a unit vector, right? Okay, so what you're going to have is minus j on the top divided by 1, which will give you the minus j, right? So the orientation over here, right, the n in this case, in fact, is minus j. And you can see that in this picture here, right? Okay, so what I did over here, so it's the same surface S here, right? So it's the surface S over here, your truncated plane. But in this case, your orientation is the orientation that you get from the RU cross RV is in fact giving you minus j, right? So the orientation for your plane over here, right, is in fact not in the y direction, but actually the exact opposite of the y direction, right? Okay, so what that means is, so this is the orientation. These blue arrows here, the n, right? These blue arrows over here, right, would be for your vector field, right? So, right, so I'm not drawing both the vector field and the orientation on the same diagram, right? So this is your S here, right? Your vector field is, all right, these blue arrows that are sort of curved in this direction, and the orientation is, this is the orientation, right, for your surface S over here, right? So this is the small n over here would be these, right? So this is the small n, right? Small n over here, right? And this here, these blue arrows, this is your vector field, right? Okay, so when you work this out, right, you want to notice, right? So remember the interpretation I said for your surface integral, what you're going to be calculating is the amount of flow that's cutting across this surface S, right? Okay, and the amount of flow that's cutting across this surface S, right? Most of the flow is basically heading in this y direction, right? But for your parametric surface S over here, unfortunately, the RU cross RV is giving me a direction for the surface S that's pointing in the opposite direction, right? So what's going to happen is that when I work this out, overall I'm going to get a negative answer, right? Because your flow isn't actually in the the opposite direction to what I want, basically, right? And you see over here, you get an answer of minus 3/4, which I will in fact work out and show you how you get, right? Okay, so that minus over here is coming from the fact that while the flow is really and is more or less cutting across your surface S over here, right, in a nicely and heading towards the Y direction, right? Your right your N over here unfortunately is pointing in the opposite direction, so you end up getting a negative answer, right? Alright, so we expect to get a negative answer, but let's actually work it out, right, using the formula specified here, right? Okay, so similar to surface integral of a function, right, usually it's a good idea to work out the RU cross RV first of all, right? So in my problem over here, the parametric surface, right? So this is formula for the surface integral that really you need to work out based on the parametric surface that's given to you, right? Okay, so the parametric surface in this case here is the RUVU, the x is equal to u, the y is equal to 1, and the z is equal to v, right? So you see it over here, x is equal to u, y is equal to 1, z is equal to v. You get the vector Ru by differentiating each of your component functions here with respect to u, right? So what you'll get is you're going to get a 1 here, you get a 0 here, and you get a 0 here, right? So 1 here, 0 here, 0 here. Differentiate to get the RV, you're going to differentiate the R with respect to v, so you get a 0 here, you get a 0 here, and you get a 1 here. So 0 here, 0 here, and 1 here, right? And the RU cross RV is, well, over here, what I have is I, and over here this works out to be K, so the RU cross RV is I cross K, and that's minus J, right? And that minus J agrees with this direction here, right? Minus J is pointing in, well, opposite direction of Y, right? And that is, right. So this is minus J, and plus J would be in the direction of the green arrow, in other words, the direction of the Y-axis, right? Okay, so that's the RU cross RV, which I would need here, right? And then the next thing you need to do is, so this is the vector field that's given to you, right? The vector field is 2xi, 3xzj, and y squared k, right? So I wrote down the vector field here. And from your definition of your surface integral, right, what you're supposed to do is, if you have your vector field here, part of working out the surface integral is where you have the x, the y, and the z here, you replace by the component functions that come from your parametric curve, right? Come from your parametric surface, right? Okay, so the x is equal to u, the y is equal to 1, and the z is equal to v. That's coming from your parametric surface. So you put that in over here for your vector field. So that is what this is saying over here, right? What this means is wherever you have the x here, you're going to replace by x of uv, which in this case the x is equal to u, right? So you put that in, right? So where you see the x, you're going to replace by u, right? So you're going to replace over here by u, right? Where you see the z, you're going to replace by v, right? So you replace the z by v. So you're going to get 3uv here. Where you see the y, you're going to replace by 1, right? So you're going to get a 1 there, right? So I get 2u, right? 3uv, right? And then y squared, which is 1 squared, which is 1, right? And I worked out the RU cross RV already. That's the minus J, right? Right. And now what I'm doing is I'm taking dot product, right? So this is dot product. If you take the dot product of the I with the J over here, you're going to get 0. If you take the dot product with K over here with the J, you're going to get 0. So, but when you take the dot product of the 3UVJ with the minus J, right? What you're going to have is a 3UV multiplied by minus 1. So you're going to get minus 3UV here, right? Okay, so when you calculate this dot product here, what you end up with is simply a function of u and v, right? And now what this is just a double integral, right? So this is double integral over region R, right? And this region R is given to you, right? Region R, when you have a parametric surface, right? The region R is specifying the possible values the u and v could take, right? And in this case, because the u lies between 0 and 1, the v lies between 0 and 1, right? And remember, this region R is going to be a region in the plane, right? Because of this form here, what you're going to get is you're going to get a rectangular region, or more precisely, what you have is a square region, right? Okay, so this, once you use your formula, right, for surface integral, right, and you put in your parameter functions, right, you work out the RU cross RV, and you take a dot product. What you simply get here is a function of u and v, right? Okay, and this is a function of u and v. So this is a double integral in the variables u and v, right? And because it's a rectangular region, we now know how to integrate it, right? You could integrate with respect to any order that you want, right? Your limits of integration, right? So here, right, so you're going to integrate the minus 3uv over this square region here, right? You could choose any order that you want, right? So here, I integrate with respect to u first and v. I want to make sure I have the correct limits. So the limits for the u over here would be 0 and 1, which come from the fact that the u lies between 0 and 1, right? Okay, and similarly the v lies between 0 and 1, so that gives me the outside limits here for the v, right? Okay, and now the rest of it is just normal integrals for, well, normal integral, partial integration first of all, right? And then you just do normal integration with respect to v, right? So this over here is what you normally do for a double integral, right? Okay, so let's go through it, right? First I'm going to integrate with respect to u. When I integrate with respect to u, I'm going to get u squared on 2 here, right? And the minus 3v is just going to come along as a constant. And then what I do is I put in my u values. U is equal to 1, u is equal to 0, right? So I'll get minus 3v on 2, right? And then when I put in u is equal to 0, I'll get a 0, right? So what I end up with over here is minus 3v on 2, right? And now this is just normal integration of a single variable. When you integrate this, you're going to get minus 3v squared on 4. And when you put a 1 into it, and you put a 0 into it, you're going to get minus 3/4 minus 0, which is this minus 3/4. Okay, so let's look at some examples that show the interpretation of surface integral, right? So I have it written down over in the notes, right? If I have a vector field, right, and the vector field represents velocity of fluid moving in three-dimensional space, right? So, for example, these blue arrows here, right, these from a vector field, and what they're doing is they're representing fluid flow, right, velocity of fluid flow. And you have a surface S, right, which is shown by this, which is an example of a surface S, is this truncated plane here, right? Then what just the interpretation of your surface integral is the net flow of the fluid through the surface S in unit time, right? Okay. Right, so your interpretation of the surface integral is the amount of flow through this surface S in unit time, right? And I think I mentioned that already, right? Okay, so this case over here, right, you can sort of see it, right? But the vector field is probably a little complicated, right? While the surface is not that complicated, right? It's a pretty simple parametric surface, right? The vector field is a little bit complicated here, right? So what we'll do is we'll look at a couple examples where we'll in fact use the same truncated plane, right? But we'll use simpler vector fields. Right, so let's take a look at this example here. Well, the vector field is yj, right? I'm going to use this vector field, but for two different parametric surfaces, right? Okay, so first of all, well, what's the vector field, right? The vector field is yj, right? So notice this doesn't have any I component or any k component, right? So this vector field is just moving in the y direction only, right? Okay, so this is the vector field yj here. I sketched it. Okay, and you want to notice that the vectors, right? So your red axis here is the x-axis, the green axis here is your y-axis, and the blue axis here is the z-axis, right? Okay, and the vectors here are just moving in the y direction, right? Okay, so what you want to notice on this side of your three-dimensional space, the y is bigger than 0. So on this side here, the y is bigger than 0, and over here, the y is less than 0, right? So if you're looking at a vector field, which is yj, right? What that means is if you, on this side of your three-dimensional space, the y is bigger than 0, so the vectors will point in the direction of a green y-axis over here, right? But over here the y is negative, right? So if you have yj, right, it's going to point in the opposite direction of your y-axis, right? So that's why these would point in this direction, and this points on this side of your three-dimensional space. The vectors here point in the direction of the y-axis, right? Which really doesn't make too much difference for us because the surfaces that we're going to consider would just lie on this side of the y-axis, at least for these examples, right? Okay, so so this is the vector field to start off with, right? And now what we want to do is we want to work out surface integral for this vector field here, right? Where your first parametric surface is given here, right? So notice here, the x is equal to 1, right? The y is equal to u, and the z is equal to v, right? Okay, so the x is equal to 1, the y is equal to u, and the z is equal to v, right? So what this is giving me is, this is giving me a truncated plane. Right, so you want to remember that this red axis here is your x-axis, this green axis here is your y-axis, and the blue axis is your z-axis, right? Okay, so first thing that you have is that x is equal to 1, right? So you have x is equal to 1 over here. Right, so x is equal to 1 is a plane in three-dimensional space, right? And you see in here, if I project onto the xz plane, right? You see in that the x is equal to 1, right? And then what you also have is you have that the x is equal to 1 over here, the y is equal to u, and the z is equal to v, right? But the u lies between 0 and 1, and the v lies between 0 and 1, which means that the y is going to lie between 0 and 1, and the z is going to lie between 0 and 1, right? Okay, so with this, so I'm expecting for my surface S1 that the x is equal to 1, the y is equal to u, but the u lies between 0 and 1, and the z lies between 0 and 1, right? Okay, so what that gives me is that it's the part of the plane where the y lies between 0 and 1, and the z lies between 0 and 1, right? Okay, so this is my truncated plane here, right? And that agrees with what I have in my diagram here, right? Okay, so if you compare the picture in the software to the picture in the notes, it's the same picture, right? This is the surface S over here is this red surface here, and the surface S, which is the same surface S1, right? Is this gray surface over here, right? So this is the S1 over here, and this is the S1 over here, right? Right, and the vector field, right? We saw already that the vector field is just going to move in the y direction, right? So this is your vector field here, right? Okay, so your vector field is just moving in the y direction, right? And you see in it over here that the vector field is just moving in the y direction, right? Okay, so for this picture here, so far this is the S1, right? Here I drew the vector field in three-dimensional space, right? But what we want to see is we want to see, well, what vectors are cutting across this surface S1, right? Okay, so this is the vectors that cut across the surface S1, and what you want to notice over here is that this plane x is equal to 1, right? It is parallel to your y-axis here, right? So what that means is that the vectors are actually not going to cut across, right? The vectors are just going to lie along your surface S1, right? So this is a plan view of the S1, and you're seeing the vectors here in the vector field, right? And the vectors are just lying along the S1 here, right? Okay, so your vectors are not lying along the S1, right? And you want to remember what your interpretation is for your surface integral of a vector field, right? It is your surface integral of a vector field has the interpretation as the amount of fluid flowing through the surface S in unit time, right? But in this case here, you don't have anything flowing through the surface S, right? It is just flowing along the S1 over here, right? So nothing is actually cutting across, right? It's just flowing along the S1, right? So in this case, for this surface S1 over here, what you expect is you expect this surface integral, right? So for your vectors over here, which are in blue over here, they're just flowing along the red surface S1 over here, so nothing is cutting across, right? So there's no flow through the S1 over here, right? And what that means is that you expect this answer to work out to 0, right? Okay, so let's actually work it out and see that we in fact get 0 here, right? Okay, and this is what I say in the notes, right? I expect that the flow through this S1 over here, because the vectors are basically just running along the S1 but not cutting through, right? You expect the surface integral to work out to be 0, right? Okay, but let's actually do the calculation, right? Let's go through the calculation. What I want to do is I want to do a surface integral of a vector field over the S1, where the vector field is yj over here, right? This is my formula that I'm going to use for evaluating surface integral of a vector field, right? Okay, so first thing that you'd want to do is work out the RU cross RV, right? So this is the description of S1 as a parametric surface. The RU you get by differentiating each of your components here with respect to U, so you'll get a J over here, right? Okay, the RV you differentiate each of your components with respect to V, right? So you're going to get a 0 here, and a 1 here, so you'll get a K here, right? So the RU is J, the RV is K, and when you work out RU cross RV, you're going to get J cross K, which is equal to I, right? You could work it out using this determinant over here, right? Okay, so first thing you need is the RU cross RV, right? Okay, now next thing that you would need is you'd need for your vector field here, right, that's given to you, what you need to do is you need to put in your component functions, right? So your vector field over here, the only thing it has is y here, right? So that's the only thing you need to replace. You replace the y with u, right? So that's where I get this uj over here, right? So replacing this y by u, I'm going to get uj, which is this uj, right? So first thing is work out the RU cross RV. Next thing is wherever you see the x, y, and z in your vector field, you're going to replace by the functions coming from your parametric surface, right? Okay, and now once you have that, you take a dot product over here, right? Right. So the uj is representing the vectors, right, from the vector field, right? And what the I is doing for you is the I is, in fact, giving you a normal vector, right? It's giving you the normal vectors or orientation for the S1, right? And the orientation for the S1 is in the x direction, right? Okay, so when you take a dot product of something that's moving in the j direction and you take the dot product of it, what's moving in the j direction or what's moving in the x direction, or if you want, you just take the dot product of the j with I over here, you're just going to end up with 0, right? So that 0 is representing the fact that nothing is in fact cutting across the surface S1, right? Okay, so here what I do is I take my dot product, I get 0. And when you're working out any integral, if you're working out an integral of 0 over here, you're going to always get 0, right? Or if you want, you can do this as a double integral where you're going to integrate 1 and 0 over here, dv du, right? So that's similar to the working that what I had over here, right? Okay, so the working that I had over here, right, where I integrate with respect to u and v, right? The inside over here is going to be 0, right? And you can check when you work it out, right? That when you actually work it out and you go through all these steps, you'd always just have say a 0 inside here, 0 inside here, 0 inside here, and you'd get a 0 over here, right? Okay, so in this case, when I work out my surface integral, I'm going to get 0, and that agrees with the fact that nothing is in fact cutting across the S1, right? Right, so let's take a look at a second example here. So it's the same vector field yj, but now it's a different parametric surface S2, right? Okay, so this is the parametric description for my S2 here, right? Now, if you want to compare to the example that I did earlier on, right? So first example I did for calculation of a surface integral, right? This was my parametric surface, right? Now, if you want to, let's compare this parametric surface S over here with the S2, right? Okay, so over here I have J here, and over here I have J here, right? Here I have the U and V lie between 0 and 1, and here I have the U and V lie between 0 and 1 over here, right? Okay, here I have U and here I have V, but over here what I have is I have V and U, right? So what I did is I switched the order of the V and U, right, as compared to this example here, right? Alright, okay, so in this example, the first example that I did, right, where it was U here and V here, when I worked out the RU cross RV to give me the orientation, I ended up getting a minus J, right? And you can see it in this picture here. Right, so this is the truncated plane S, right? And these blue arrows over here indicating, right, that the orientation is, okay, in the direction of minus J here, right? Okay, so that's when I worked out the RU cross RV in this case, right? But when I work it out for this parametric surface, because the V and U are in a different order, right? What's going to happen is when I work out the RU cross RV for this parametric surface where I have the V for the I and the U for the K, right? What I'm going to get in this case is, so this is for the S2, right? So let's look at the working for the S2. Right, so the X is equal to V, and the Z is equal to U, and the Y is equal to 1, right? Okay, so when I work out the RU cross RV in this case, right, the RU, okay, so I'd need the RU, right, and to get the RU, I need to differentiate with respect to U, right? So I differentiate the component functions with respect to U, right? I can do it over here with respect to U. I'll get a 0 here, I'll get a 0 here, and a 1 here, right? Which is this 0 here, this 0 here, and this 1 here, right? And then I'm going to differentiate with respect to V, right? And this is for the S2. When I differentiate with respect to V, I'll get a 1 here, I'll get a 0 here, and a 0 here, right? So I get an I, right? Okay, so here what I have is I have a K, and over here I have an I, right? And then the RU cross RV would give me K cross I, and in this case what I will get is J, right? Okay, so you want to compare, this is the very first example that I did, right? And the RU cross RV, when I worked it out, was I cross K, which is minus J, right? And that gave me this orientation here, right? That pointed in the opposite direction of my y-axis, right? Right, but in this case, what I have is the V for the S2, right? The parametric description. Now the V is, I exchanged the U and the V, right? And because I exchanged the U and the V, right? When I work out the RU cross RV, right? The order switches here, right? The order switches from I cross K to K cross I now, right? Okay, so while these as sets did the same thing, right? In this case, the truncated plane, right? The orientation is not going to be in the direction of minus J, right? The direction is in fact going to be in your positive Y direction over here, right? Okay, so that's one thing to note, right? the parametric, you can have parametric surfaces, right? And where the u and v are specifying the same surface, but because of the order of the variables and so on of the u and v, right, the orientation can change, right? And that is what happens here, right? But let's just go ahead and work out the surface integral over S2, right? And we'll see what the answer is. Right, so we want to work this out, right? So we want to work out this surface integral where for the S2, right, where the vector field is yj and the S2 is specified parametrically here, right? Okay, so you'd need the Ru and the RV, right? So remember what you're doing is you're going to be using this formula here to work out my surface integral. And part of the formula is calculating the Ru cross RV. Okay, so I'd need the Ru cross RV, and I in fact already worked that out, right? So the Ru is going to work out to be 0 here, 0 here, and I get a K, right? The RV, I will get a 1 here, 0 here, and a 0 here, so I'll get an I, right? And the K cross the I will in fact work out to be J, right? So Ru cross RV is J here, right? Okay, and I'm using this here. This is my definition for surface integral of a vector field, right? The Ru cross RV, I worked it out already. It's J, right? What I need to do now is I need to put in right. So for my function for my vector field, which is yj, right? I'm going to put in. So this definition here, what this means is that where you have the x, y, and z here are replaced by the component functions, right? X is equal to v, y is equal to 1, z is equal to u, right? So the x is equal to v, y is equal to 1, and z is equal to u, right? So what I need to do now is I need to replace the x, y, and z in my vector field by these component functions, right? But the only thing that I need to replace is the y, right? So the y, I replace the y as 1. So I end up with just 1 times j, which is j, right? So when I replace the y is equal to 1 in my vector field, I'm going to get this j over here, right? Okay, so the Ru cross Rv is j, right? The vector field on the surface S itself, right, is actually just j, right? Okay, so the picture is this, right? Okay, so this is the picture, right? And in this case, the n and the f are actually the same thing on the surface S, right? Okay, so right, you see, and so this over here, this is the vector field, right? The vector field is j, right? And the n here, which is the normal vectors, right? Which is the orientation, right? That is also j, right? Okay, so both of those are j over here, and the vector field j on the surface S is shown here, right? Okay, and it's S2, right? So the surface S that I'm looking at is S2, right? And the j is, this is the j here, right? Okay, and if you project down this way, you'd see that it's in the direction of your y-axis, right? So both the f and the n are the same in this case, right? All right. Okay, so you take your dot product over here. Take the dot product of the j here and the j here. Take the dot product of j and j. You're gonna get 1, right? And what you have here is now a double integral of 1 over your region R, and the region R is a rectangular region. And how you know it's a rectangular region? That came from your parametric description here for the S2, right? The u and v. A line between constants 0 and 1, so that tells you that this region R here is rectangular, in fact it's square, right? And now you just do, if this is a double integral over a rectangular region, you just integrate this in a normal fashion. You could integrate with respect to u first, then with respect to v. Limits for the u would be 1 and 0, limits for the v would be 1 and 0, right? Okay, and you integrate first with respect to u, you're going to get u, you put in the 1 and 0, you get 1 here, and then you integrate the 1 with respect to v with limits 1 and 0, and you'll get a 1 there, right? Okay, so in this case, your surface integral turns out to be equal to 1, right? So if we go back to our diagrams, right, that's in the notes, right? In this case here, right, for your surface S2 and for the same vector field, which is yj, right? Notice in this case, the vector field is in fact actually cutting across the S2, right? So you do have flow across the S2 over here, right? And because the orientation of this S2 is now in the y direction, right? The flow across is regarded as positive, right? And so I'm going to get a positive answer, and that positive answer is actually equal to 1 in this case. Let's recall for surface integral of a function, right? So not a vector field, but a function that we saw previously, right? The surface integral of a function. We have two ways to calculate it based on the type of surface that I have, right? So if the surface S is a parametric surface, right, then what you would do is you'd use this formula here with the RU cross RV, right? Okay, and if your surface S is living in the graph of a function z is equal to g of xy, right, and you project the S to get a region R down here in the xy plane, right, then you can use this formula involving the g of xy, right, to work it out, right? Okay, but these are for surface integrals of functions, right? And it turns out it's a similar sort of process, at least in this class for us, when we integrating surface integrals of vector fields, right? So if you're going to integrate a surface integral of a vector field, and we saw 3 examples of this so far, right? Then the formula that you would use is you would use this over here, right? Okay, so notice this has RU cross RV, right? And this is if the S is given to you parametrically, right? But if the S is not given to you parametrically, and if the S is given to you in this fashion, as living in the graph of a function z is equal to g of xy, right? Then what you have is you have a corresponding formula, right, for surface integral of a vector field, right? Okay, and the formula is stated here, right? Okay, so this is our setup over here. Now this is very similar to the setup that we have across here, right? You're going to have a surface S, right, which is a dark gray surface, lying in the graph of a function z is equal to g of xy, right? And what you're going to do is you're going to project this S down onto the xy plane to get a region R, right? The only difference in between this setup and this current setup that we need for vector fields, right, is we'd want the surface S to have an upward orientation, right? So remember, when you're working out surface integral of a vector field, right, it makes a difference what the orientation of the surface is, right? If this was say pointing downward, then what you get is a negative answer compared to when it was pointing upward, right? Okay, so we're looking at surfaces S that have an upward orientation, right? And the idea here is that your graph of your function, right, the graph of your function over here, because it's a graph of function of 2 variables, right, it has a basic sort of like a overall kind of horizontal aspect to it, right? Okay, and because it has some sort of like overall horizontal aspect, you could talk about upward and downward relative to the graph z is equal to g of xy, right? Okay, so next picture, if you want, of upward and downward orientation would be this, right? Okay, so this here is a surface S here, right? This is an example of when it has upward orientation. And this surface S over here, this is an example of when it has downward orientation, right? So for the purposes of the formula that's going to follow this setup here, right? We're going to assume that the surface S has an upward orientation, right? All right, so the setup is we have a graph of a function g of xy, which is this g of xy over here, right? So the light gray part surface here is the graph of the function. We have S that is formed, that basically is a subset of this graph of your function g of xy. So the S is the dark gray part over here, right? R is the projection of S, right, into the XY plane. So when you take S and you project it in the XY plane, you get the R here, right? Okay, and you assuming that S over here has an upward orientation, right? The orientation of S is chosen to point upward, right? Okay, so for this formula, right, what you want to do is we want to specify, we want to call the X component of the vector field capital P. We're going to call the Y component of the vector field capital Q, and going to call the Z component of the vector field capital T, right? We don't want to use P, Q, and R, right, because we're going to already use R over here for the region in the XY plane, right? So we call this one T, right? Okay, so if I want to do a surface integral of a vector field, right? So some vector field that's cutting across this graph or this surface S here, right? And where I'm going to assume that S has an upward orientation, right? Then the surface integral of a vector field F over this S here, right, is given by minus P dg dx, right? So remember the G is the graph of this graph is the graph of a function G of xy, right? So this is your function G of xy. So you have minus P dg dx, right? Minus Q dg dy, right? Plus T over here, right? So it's minus the x component of your vector field times dg dx minus the y component of your vector field times dg dy plus t over here, right? Okay, and notice the p, the q, and the t, right, are all functions of x, y, and z, right? Right, so this formula here with the minus p dg dx and the minus q dg dy plus t, right, for inside this double integral, it would require a little more detail than what I have here in the notes, right? Okay, so remember what you're doing is you integrate in your vector field over your parametric surface S here, right? Okay, so vector field has, it's in terms of the variables in the vector field would be x, y, and z, right? Okay, and part of this formula is your vector field you write as p x, y, z, q, x, y, z, and t, x, y, z, right? Okay, so on this right hand side here, right, it'll be minus p, right? So the same minus p as I have over here, x, y, right? But if you had any z in this p of x, y, z, right? Remember, in you're gonna have a function g of x, y, right? And this function g of x, y is zg of xy, right? So in this p x y z, right, what you're going to do is you're going to replace this z by g of xy, you're going to replace this z by g of xy, and likewise you're going to replace this z by g of xy, right? Okay, so hence you get this formula here, right? So it's the same formula as this, except that this one has more detail, right? So the idea here is that with this p, which is x, y, z, right, what you're going to do now is you're going to make sure that you replace this z by the g of xy, right? And this formula here is the same as this, but with more detail. So let's do this surface integral of a vector field where your surface S actually falls into this case here, right? Where it's the surface S is going to be part of the graph of a function, right? Okay, so in this case, the surface S is a paraboloid, right? Which is z is equal to 1 minus x squared minus y squared, right? Right, so let's recall what your parabola z is equal to x squared plus y squared is, right? So your parabola z is equal to x squared plus y squared. It's what you would get if you just took a normal parabola, so just with the lines over here, right? And you rotated it about your z-axis, and what that would do is that would sweep out a surface for you in three-dimensional space, right? I think we saw this already. Z is equal to x squared plus y squared, right? Okay, now z is equal to minus x squared minus y squared is when you take the negative of this, right? So what that does is z is equal to minus x squared minus y squared. What would happen is that this would be reflected in your plane z is equal to 0, right? Okay, so you see in it there, right? When you reflect the this parabola z is equal to x squared plus y squared, right? What you would get when you reflect this in your plane z is equal to 0, you'd get your parabola z is equal to minus x squared plus y squared, right? Okay, now what you want to do is you have 1 minus x squared minus y squared in the problem. So what you're going to do is you're going to take this and you're going to translate it up by 1 unit, right? Okay, so what you had was the minus x squared minus y squared, and you translated it up by 1 unit, right? Okay. Okay, so this is what I have, right? And what they asked me in the question is, you want the part of the paraboloid that lies above the plane z is equal to 0, right? Okay, so the part that lies above the plane z is equal to 0 is, well, it's this piece over here, right? So it's what's above your plane over here, right? Okay, so it's this top piece over here that's above my xy plane. This is going to form my surface S for me, right? And you want to notice this surface S over here is part of the graph of a function, right? So this is the S over here, right? So if we want to compare our general picture, you have S, right, which is part of the graph of a function, right? Okay, so in this case over here, we have the S here, which is the top part here, right? And that is part of the graph of the function. The entire graph is what's going down there, right? So it keeps going down, right? Okay, so my surface S is the part of your paraboloid 1 minus x squared minus y squared, right? That lies above the xy plane, right? So we're looking at this piece above the xy plane. Okay, so that's the diagram there, right? Of the paraboloid 1 minus x squared minus y squared that lies above the plane z is equal to 0, right? Okay, now so we're going to use this formula here with the g of xy, right? Now part of this is, well, I have what the s is already, right? The s is the part of the paraboloid, right? I have what the g of xy is because that's given to me, right? The z is equal to g of xy, right? Okay, and what I would need is the region R, right? And how I get the region R is I take this, the S over there, and project it down onto the XY plane, right? Now, because of the symmetry of the paraboloid, right, when I look down along the x-axis, right, what I will see is I will see a disk, right? I will see a disk of radius 1, right? Okay, so first of all, what I'm seeing is I'm seeing a disk when I project down, right? So I'll see this disk when I project this S onto the XY plane, right? The question is, well, what's the radius of that disk, right? Now, the radius of the disk is contained inside this circle over here. And this circle is where your paraboloid 1 minus x squared minus y squared intersects the xy plane, right? The xy plane, remember, is the plane z is equal to 0, right? So to get this circle over here, what you do is you solve simultaneously the equation z is equal to 1 minus x squared minus y squared. Okay, and the equation z is equal to 0, right? And when you solve those equations, so I have z is equal to 1 minus x squared, which is one equation. Then I have a next equation, which is z is equal to 0. In order to solve those simultaneously, I put 0 in for z, and I get 0 is equal to 1 minus x squared minus y squared, which gives me this circle over here. And remember, this circle over here is x squared plus y squared is equal to 1, right? With the additional information that the z is equal to 0, right? So it's saying that it's a circle of radius 1 here, right? X squared plus y squared is equal to 1, right? Coupled with the fact that the z is equal to 0, right? So it's a circle of radius 1 that lies in the plane z is equal to 0, right? So that is how you're going to get this bounding circle for your disk here, right? Okay, so when I project down, I will see a disk, right? And the disk would look like this here, right? And the bounding circle would be x squared plus y squared is equal to 1, which is this over here. Right? Okay, so the surface S is the part of the paraboloid that lies above z is equal to 0. Right? To get your region R, you project S onto the xy plane, so you'd get your region R over here. Right? Okay, so in this case, the region R would be a disk of radius 1. Okay, so now I know what the S is, I know what the R is, and I know what the g of xy is. The g of xy is 1 minus x squared minus y squared. Right? Okay, right, so I have that information so far, and now what I do is I use my formula for the surface integral, right, of the vector field, right? And this is what I'm using here, right, with the minus p, the minus q, and the t over here, right? Okay, part of this formula is that need dg dx and dg dy, right? Okay, so the g of xy is 1 minus x squared minus y squared. Okay, so I have it stated here, right? The g of xy is 1 minus x squared minus y squared. So the derivative of g with respect to x gives me minus 2x, which is this over here. Right, the dg dy, right, over here, right? I take the g and differentiate it partially with respect to y, so I'm going to get a minus 2y, which is this minus 2y over here, right? Okay, and each of these, what you're going to do is the function p, right? So the function p, q, and t are coming from your given vector field, right? And your given vector field is x, y, z, right? So the p, the capital P is equal to x. The capital Q is equal to y, and the capital T is equal to z here, right? Okay, so for each of these, the capital P, the capital Q, and the capital T, right, when you're working with this formula, you'll keep the x and the y, right? But wherever you see the z, you're going to replace the z by g of xy, right? And the g of xy is 1 minus x squared minus y squared, right? Okay, so when I'm replacing, so this is the p over here, and p, it's minus p dg dx, so I have minus x dg dx, which is minus 2x, right? And then the q is y, right? So I have minus y dg dy, which is minus y by minus 2y, right? Okay, and then the t in this formula is z, right? So I'm going to have the t over here. That's part of this formula, right? But notice what this says is wherever I see the z, I'm going to replace the z by g of xy, right? So this is z over here, right? And I have it written over here. But this z I need to replace by the g of xy, and the g of xy is 1 minus x squared minus y squared, right? So going from here to here, I replace the z by 1 minus x squared minus y squared. Okay, so now I have this over here, right? So this is a double integral over region R in the xy plane, right? And before I start integrating, what I can do is simplify this, right? So what I have is plus 2x squared here, plus 2y squared, right? And that will cancel with the minus x squared and the minus y squared to give me x squared plus y squared, right? So that is what happens over here. I have x squared plus y squared. And then I have this 1 from over here, right? Okay, so I have 1 plus x squared plus y squared, right? So what my surface integral worked out to be is my surface integral worked out to be a double integral of 1 plus x squared plus y squared over region R. And the region R is a disk in the xy plane, right? Okay, and if you have a disk, right, you should know by now that the best way to do this is using polar coordinates, right? Okay, so to evaluate this double integral, we're going to use polar coordinates. Okay, so your polar coordinate conversion is described over here. This is the formula for your polar coordinate conversion when you're doing a double integral. So your x you're going to replace by r cos theta, which I do over here. The y you're going to replace by r sine theta. You'd have this extra r over here, and then you're going to integrate with respect to r and theta. Your limits of integration come from describing this disk over here as a polar rectangle. Remember, your description of this disk as a polar rectangle is that the theta goes between 0 and 2 pi, and the r goes between 0 and 1, right? So you need to express this region, this disk over here, as a polar rectangle, because these will form the limits of integration when you integrate with respect to r and theta, right? Right, so the integral with respect to r, right, your limits would be 0 and 1, which come from the description as a polar rectangle, right? The limits for the theta come from the theta lying between 0 and 2 pi here, right? Okay, so now I have my limits of integration for the r and the theta, right? What I need to do now is I just simplify this, right? So here what I could do is I could factor out the r squared, right? I have cos squared plus sine squared, which means that I just have r squared here, right? Or if you want, you could remember that x squared plus y squared just works out to be equal to r squared when you do the conversion to polar, right? Right, so this integral here simplifies to this, and now what I need to do is I need to do the inside integral, which is with respect to r. In order to integrate this, I just simply multiply it out. So I have r plus r cubed here. When I integrate the r, I get r squared on 2. When I integrate the r cubed, I get r to the 4th on 4. I'm putting in r values 1 and 0, right? Okay, and when I put in r values 1 and 0, I'm going to get a half plus a quarter, which is 3/4, right? Okay, and then finally you integrate this here with respect to theta, which would give you 3 theta on 4, right? And then you put in your 2 pi, right? So that would give you 3 times 2 pi divided by 4, which is 3 pi on 2, which is the answer.